Welcome back to infrared spectroscopy. We're going to see how the machine does it for you, okay? Here's just a schematic diagram that shows you what's inside one of these machines. A picture of the machine is right here. So it looks just like a box, okay? And you can actually lift it. It might be like 20 pounds. So they're not really heavy. Nowadays you can have even much smaller ones that you can just carry along like a lunchbox. All right, so let's look at let's open it up and look inside. You need to always have a source because this is a spectroscopy, which means you have a spectrum of electromagnetic radiation, and you're going to only emit a certain region. You're either emitting UV waves region or infrared region or radio wave region, so you're only emitting a certain region, so you need a source specific to that. For example, if you want to emit heat, infrared, you want to have a wire that will emit infrared or heat radiation below the red. So here they will have a silicon carbide wire or some wire that will emit in the infrared region. Okay, so then that is going to then go into this machine, and there are mirrors here that will separate them into two different beams. So the source is here, the radiation comes in, the mirror separates them into two beams. One beam is going to go up and one beam is going to go down, or if you're in a mirror inside a machine, it's going to be parallel. Okay. The top one is where you would put a empty cell. So a cell is just a little sample container. The bottom one here is where you would put a sample inside the same cell. Okay, and then the beam goes right through, and there is a chopper. The chopper, think helicopter chopper. So it's rotating. And at one point it's letting the sample beam through, and at another time it's letting the reference beam through. So it's alternating between the sample beam and the reference beam. There's a motor there on top that rotates this chopper. Okay, and so what you do is you turn a machine on, you have your infrared coming out. You first have to prepare your sample. Before you do that, you take 2 potassium chloride pellets. There are many ways to do it depending on what kind of machine you're using. So let's say you take 2 potassium chloride pellets, you put a drop of sample in here, you slap it together, make sure there are no air bubbles, and then you would put it right in the face of the beam. So on the top one, you would put the cell without the sample. So then your radiation goes through the reference, and then it'll take in all that information. There may be carbon dioxide, there might be water, air, and absorption of infrared due to this cell. Then it'll go through the sample, and the sample would have different types of bonds, CH bonds, CO bonds, whatever, nitrogen, NH bonds, whatever bond. Those are going to absorb the radiation, and so then when it goes through, it'll alternate, and here you'll have like a prism or a grating, and the grating is going to take that. It's like a rotating grating, and it'll just take that and fan it into this detector slowly, so all of the radiation goes through. Okay, this is a dispersive IR. Now they have FTIRs, which are much better. You have the detector right here. And so the detector will take in the information that comes through the sample cell and the reference cell alternately, and then it will detect all of the radiations that are coming through, and then it'll go to a computer where it'll process it, and you will get an output. So over here, what you're actually seeing is the amount of transmittance that's coming out. So let's say here's your infrared coming from the source, and then you put your sample in, and your sample is absorbing some of that. Okay, so here's your sample, potassium chloride pellets, and your sample is in here, it's absorbing it, and then you get an output. Obviously, it's going to be different from what went in because some of it's absorbed by the molecules. So we can see what's absorbed by the molecules. So let's say this is called the reference or intensity of the reference here. And this is going to be, let's say, coming out of the sample. And so reference is this top peak or beam, and this is the sample beam. And so the percentage transmittance can be calculated by finding both of these, and that's going to be I sample. The machine's going to do this for you over I reference times 100. Okay. So whatever the molecule doesn't absorb is what comes out. So you can find out what's the percentage transmittance. So here I is just the intensity. Okay. So intensity is measured on the y-axis of a plot. And the x-axis is the wave number. So this is going to be your wave number. We talked about it, 4,000 to 400 centimeter minus 1. The intensity is really, I mean, on this scale, you're going to have percentage transmittance. But what we are actually seeing is how much the molecule absorbs. So for transmittance, this is 100 and 0. So the absorbance is going to be going in the opposite direction. The more transmittance you have, that means the less absorbance you have. Or the less transmittance you have, the more absorbance you have. So over here, let's say you have a peak here. This is always, you'll have your CH peak. And then let's say you have a very high peak like this in 1700, let's say for a carbonyl. Here, this is coming all the way to 0. That means almost the transmittance is almost 0 here. That means the molecule really took it all in. So transmittance is inversely proportional to absorbance or absorption by molecule. All right. So certain bonds will absorb a lot of infrared, and it so happens that if you have a polar molecule, the more polar it is, the more intense the absorption is. Some molecules are infrared inactive. They are totally nonpolar, and they are also symmetric. So for a molecule to be active in infrared, it has to have a dipole. So dipole moment of a molecule would actually increase absorption. Certain bonds absorb at a lower wave number. Let's look at that. All right. All right. So as we saw over here, the machine, the detector is a thermocouple detector, which is perfect for infrared. The thermocouple detector then senses that and converts that to an electrical signal and transmits that to the computer, and the computer then does a calculation and finds out how much has been absorbed and how much has been transmitted. So we can see that the percentage transmittance is on the y-axis, and then the wave numbers on the x-axis. Okay, the wave numbers are constant, and they would correlate to a specific type of a bond, a CH or a CO or a bend and so on. So each one of this is a vibratory mode. That is a constant that we cannot change regardless of what type of sample cell we're using, whether it's a solid or a liquid or whatever. Okay, if it's a liquid cell, then you'll have the empty cell on top, and you'll put a with the solvent, and at the bottom you would have the solvent plus the sample. So then it will filter out all of the radiation or infrared that comes out of the solvent from the sample. So you'll only get information on the spectra about the pure sample. Okay. Now, as we saw before, as the transmittance goes up, that means a lot of it's transmitted and not absorbed. So transmittance goes up, absorbance goes down, transmittance goes down, absorbance goes up. So even though we say this is a peak where the transmittance is concerned, that's actually the minima, okay? But where absorbance is concerned, absorbance is 1 over transmittance, inversely proportional to transmittance. So this is where the maximum absorbance is, and this is the minimum. So then you can see that certain peaks absorb a lot more than others. And why is that? Why is it that certain peaks are a lot longer or have maximum absorbance and minimum transmittance, whereas certain other peaks let all this IR go through the sample cell and only absorb a little bit? There are many factors, but one of the most important factors is the dipole moment of the molecule. Okay, there's resonance at play, there's lots of different things, but the most important thing that governs how much is absorbed is the dipole moment. So when the dipole moment of a molecule increases, then the absorbance increases. For example, if you take a carbonyl, a CO, this is very, very polar, CO double bond, because you know pi bonds are polarizable, and it's also a double bond, it's strong, so it absorbs a lot of infrared radiation at this frequency. The frequency doesn't change at all, whatever the conditions. The frequency is a constant, which is why we can use that to detect what the molecule is. So here the dipole is high, so therefore the absorbance is high. Okay, so dipole increases, then absorbance increases, and transmittance is then at a minima. And of all the peaks in infrared, the carbonyl is the strongest or the most intense peak. Now some peaks, some molecules are infrared inactive if they have zero dipole. So dipole is 0, then you have 0 absorbance. It's almost like the infrared doesn't see the molecule, it goes straight through. The amount coming through the reference beam, amount coming through the sample beam are the same. Okay, so it's like 100% transmittance. And an example of that would be like an alkyne. Let's say you have the same number of carbons on both sides, it's perfectly symmetric, 0 dipole, 0 absorbance. So this is IR inactive. So it's pretty much the opposite of something like this. It's almost 100% absorbed at that particular wave number. All right. So let's look at some of the other things that influence the wave numbers of this absorption. What are the things that really influence whether it's absorbing infrared radiation at 3000 or 2000 or 1000? What are the things that decide that? Let's look at that for a minute. All right. Let's go back and see where all of these bonds are going to absorb and why. The reason why. That's the most important thing that we're going to look at. Why is it that certain bonds are doing around 4,000 towards 4,000, certain bonds are absorbing towards 400 centimeter minus 1. So why is that? Well, let's go back to our calculation for your wave number, right? So we saw that it's 1 over 2 pi c, where that's the speed of light, k, force constant, which shows the higher the force constant, the stronger the bond, and mu is just the reduced mass, which is mass of one times the mass of the other over mass of this plus this. Okay, so you can see how when the mass goes up, the wave number will go down. And that's what we are seeing. Let's look at the trends here. Let's look at what happens when you go from a CH to a CO to a CBr. So hydrogen is small, oxygen is a little bigger, bromine is enormous. Okay, so well, when you have bonds to huge atoms, then your bonds are going to be longer. So as bond length increases, so here we're going to talk about this reasoning here. As bond length increases, then your bond dissociation energy goes down and bond strength goes down. Bond strength decreases. That means K is going to decrease, which means their wave number is going to decrease. So K decreases and wave number frequency also is proportional to the wave number. We saw that of absorption also decreases. So that's why you can see this trend. All right? As the atoms get bigger and bigger, then they're getting weaker, and so the frequency of absorbance decreases. Stronger bonds will absorb at a higher frequency than weaker bonds. All right? Let's look at the reasoning for this. So this is about bond length. The first one is about bond length. Another trend that we see is due to bond multiplicity. Okay, so let's look at why that is. So when you have a single bond, it's about CC single bonds about a 1200. It's rarely seen. It's very weak. Intensity is weak, but the number is 1200. CC double bond is 1660. That's about like medium. Okay, and CC triple bond is 2100. That's also medium. But you can see that the number increases. That means the frequency of absorbance is increasing, or the wave number of absorbance is increasing. Why? Because it's a lot harder to stretch a double bond than a single bond, and it's a lot harder to stretch a triple bond than a single bond. So well, let's look at another reason, bond multiplicity. So when the bond multiplicity between two identical atoms increase, then the frequency of absorbance also increases. Okay, bond multiplicity between two identical atoms, atom increases, then, well, it's like this. If you had a single bond, you'd need some energy to stretch it, but if you had a double bond, you'd need a lot more energy to stretch that. And then if you had a triple bond, then, you know, it's going to be even more than that. The more bonds you have, the stronger the bond and higher the K, or the force constant, then your nu, or your wave number, is going to increase, and wave number increases. Okay, so always for the same atoms, Single bond will be lower than double bond will be lower than the triple bond. Bond multiplicity increases, wave number increases. That's kind of across the board. Let's look at reason number 3. So that was number 2. Let's look at reason number 3 for different wave numbers for different functional groups or different types of bonds. All right. So here you can see there's a CN, CO, and CCl. All right. Nitrogen has 1 lone pair, oxygen's got 2 lone pairs, and chlorine has 3 lone pairs. The more lone pairs you have, the more electron repulsion you'll have. So therefore, when you have electron repulsion, then the bond also gets, in this case, kind of weaker for single bonds. So CN absorbance is about, well, 12,000 to 1350, whereas CO is about 1050 to 1150, and there too tertiary would be more than secondary, more than primary for the CO bond, and then you would see CCl is a lot less, 850 to 550. All right. So the number of lone pairs increases, then the repulsion increases, and therefore the bond dissociation goes down as the bonds get a little weaker, and then also you would have the K going down and the nu going down. All right. So number 3, as lone pairs increase, repulsion increases. So between the bonds and the lone pairs here, and therefore that makes the bond weaker. K goes down, and then frequency goes down. All right. Let's look at another very important factor. Here's a triple bond CH, a double bond CH, and a single bond CH, and you can see that the wave numbers are going down. They're all in the 3000 region. But triple bond is a lot higher, 3300 around. A double bond is about 3100, and a single bond is about 3000. What's different about them? The only thing that's really different about them is really the hybridization of those bonds. So triple bond is an sp, then sp2, sp3. So number 4 is going to be hybridization. Why is that? Think about it for a minute. Hybridization also plays an effect on where the peaks are going to show up or what frequency they're going to absorb at. So here an sp is more than an sp2, more than an sp3 for the CH bonds. Okay, so we're talking about the same type of bond in all of this. They're not different bonds, it's the same type, but this is a lot higher. Well, if you take sp, the S character is more, which means when S character increases, it's more spherical. So spherical nature of the orbital increases orbitals. So then therefore you'd be closer to the nuclei. And if it's closer to the nuclei, it's also got more attraction from the nuclei. So its bond dissociation energy is higher for SPCH versus SP2CH versus SP3CH. And that's also a known fact. So therefore the K is going to be higher here than here than here. And because in SP3 there's more P character and the bond, the CH is a little further away from the carbon nuclei, and therefore it's not as tightly held. So therefore the bond dissociation energy there is lower, which means the K is lower, and therefore nu is lower. So bond dissociation higher, K is higher, and therefore frequency is higher. All right. More P character, then K is lower, and nu is lower. Here K is higher, nu is higher. So that's a very good way to look at it when you have the same bond with different hybridizations. And the last one here talks about electronegativity. And when you have electronegative atoms, the dipole moment increases, the intensity increases. We already saw that a carbonyl is very intense, but these are that intense. But also where it absorbs, not just how big or how long the peak is, but where it absorbs also changes when you go from a lower dipole to a higher dipole. And that's because, you know, when you have a double bond and a pi bond with a more electronegative atom there, the polarizability is higher, and so the bond gets stronger there with the pi bond, and so therefore you would have a higher K and therefore a higher nu. Delta En is more, K more, and nu more in a double bonded series like this. All right, so those are the reasons that we have seen. For some of the reasons, there are more, and we will come back and we'll actually look at spectra and we will see these trends. All right, in summary, let's say you have a sample here of something that you want to know. You know, you're curious to know what's inside. What is it that they're putting in your juices? Take a little bit, put it on a potassium bromide pellet, put it in your machine, and run it. And when you get these peaks, we have a table. The table will tell you what functional groups will absorb at what frequency or wave number in this case. And from that, you can identify what type of molecules you have. Do you have alcohols? Most probably you do, because even sugars have alcohols. Do you have carboxylic acids? Most probably you do, because citric acid is found in most food items. A huge mixture like this would be you'd have all kinds of peaks, but when you purify this and take out the components and put them on a disk, then you would be able to identify them. So when you have a spectra like this 4000 to 400, most of the valuable information is going to be between 1300 and 4000. Below 1300, it's going to be pretty much called the fingerprint region. Okay, so 4000 to about 1300 is where you'll see most of the main functional groups. 1300 to about 400 is called the fingerprint region. So let's say the forensic, the police department runs a sample and they want to know what it is. They'll go through a library and try to match this perfectly on top of a known IR. If it matches perfectly, then that's it. That's how you identify it. Okay, that's fingerprint. This is mainly to figure out what kind of functional groups there are. And the reason why different things absorb at different frequency is because of their bond structure. If you have longer bonds, they're going to be absorbing at lower frequency. If you have multiple bonds with the same atom, they're going to be absorbing at higher frequency. If you have fewer lone pairs, they're going to be absorbing at a higher frequency. If you have more S character, they're going to be absorbing at a higher frequency. And if you have very polar pi bonds, they're going to be absorbing at a higher frequency. So knowing all of this, we will be able to decipher all of the functional groups in your molecule, which is the target, okay, which is the goal of infrared spectroscopy. All right, let's look at our spectra next time. See you soon.